We said at the beginning that one of the purposes of this course was to explore ways of representing and storing and finding relationships and massaging and doing all the things that need to be done to data. And so what we're finding with relations is that this touches on many of the most common practices in data uh, representation and data arrangement and data manipulation. And so this is really kind of a core topic. And so let's keep going with it. One of the things that you might keep in mind is the human brain. And right now, the best ideas in physiology about how the brain works, and these have now been around for a few decades, so they're not some flaky um, idea. And the idea is that the brain cells don't actually contain information. What they do is provide a place for the connections, and it's the connections that store the information and manipulate the information. And it's the connections that change in terms of how learning occurs. And so when you're talking about connections, you're talking about a cell A and a cell B, and there's an edge between them. There's actually literally an edge between them. And so that means that there's a relation there. We've got an ordered pair, the origin cell, the target cell. And so this is very much tied up in almost everything that we do with data involves some kind of relation. So remember, a relation is a subset of a Cartesian product. And so this is the definition. So you have the Cartesian product of two sets, and this is very abstract. We're not saying anything about the sets, and we have some subset of their product, and we'll just call that R for relation. So that's pairs AB. Now, the book does something that I find almost offensive, which is that they say this is a relation from A into B. And I don't think that's correct. And so there are a lot of good things about this book, but this isn't one of them. So there's just, when you say there's a relation, it's just a subset of the Cartesian product of two sets, and you really can't go any further than that. So one of the ways that we represent relations is with directed graphs. So a directed graph has nodes and then from A to B, just like in here. And so you have here's an element of the relation, here's an element of the relation, so forth and so on. So let me draw one just to give us something concrete to look at. For the moment, I'm not going to label the nodes, but I am going to indicate the direction that happens. So this bottom one here is connected to this one, and this one's connected to this one, and so forth and so on. So an arrow from a node A to a node B indicates that A comma B is a relation, is an element of that relation. So, and there's a situation. Now, if we have a relation on A cross A, so A is some set, and you've got pairs of things from A. So when you think about just ordinary graphs like you would do in algebra, that's a relation on R, the real numbers, cross R, and you get some subset up here, or it might be some swirly thing. We talked about that. So this can be represented by a matrix, and so the idea is if you enumerate the elements A1, A2, A3. This only works really if you have a finite set. So I've just listed the elements in a finite set. And so the cardinality of this set A is n, using the notation that I just used here. And you define a matrix by the ij entry is 1 if A sub I, A sub j is in the relation, and 0 otherwise. So there's the strict definition, and Now here we've got 6 things. So this would be a 6 by 6 matrix. This is already getting awkward to write down what the matrix is. The matrix is more of a conceptual tool rather than a computational tool. But concepts are good. Concepts take us a long way. This is also more of a conceptual tool than a computational tool because the pictures, I mean, if you have a set with 4 bazillion elements, then you're going to have 4 bazillion dots, and I don't have enough paper in my house to cover that. So, so these are, so we have some pictures or some computational tools to think about relations in our heads, but that's not how we're actually going to work with them. That's okay though. So there's an important thing that we can do with relations, and this becomes super important when we talk about functions, which is the next topic. And so the idea here is that we can compose relations. Now, compose is a funny word. It's a mathematical word. So what we mean is we're going to look at one thing and then look at a different thing. And the kind of the model that you want to use for composition is, let's take a simple idea from algebra. We have some function, and I'm writing out a formula for it. So in algebra, a function isn't the formula, it's what it does. The formula is what it does to the input x. So here's something, you take 1 minus x squared. So you can do all kinds of algebra stuff with this. You can graph this or find the roots or whatever. But we just want to look down and see what's happened here as a function. And the way this function acts on any input is it squares that input and then, that's the composition word, squares the input and then subtracts it from 1. So you square the input, then, and then is the big word, subtracts from 1. So squaring is a function. Subtracting from 1 is a function. And so this poor x has had 2 things done to it. It got squared, and then it got subtracted from 1. I think the subtracted from 1 is the more painful one, but that's the way it goes. Anyway, so compositions are very important in looking at functions and various kinds of algebraic and other expressions. And so that is the model for what we're doing here. But we can do all kinds of relations. Now, you know, when we start talking about this, it's going to start to be kind of abstract. And so what we're doing here is the following. So let me just write this out in a formal abstract manner. This is not designed for you to understand it. This is designed for people to prove theorems about it. So, but we need to try to understand it, and that's what's going on here. So here's what happens. If we have a relation R in the product A cross B, so we have some subset of A cross B, and we have a relation S, which is in B cross C. So the things in R are ordered pairs, something from A, something in B. And the things from S are ordered pairs, something in B, something from C. And when we compose them, that is going to give us a subset of A cross B. I'm sorry, I said the wrong thing. Skip that. A subset of A cross C. So we get a new relation in A cross C, and the formal definition is this. So first of all, we're going to call that relation SR. So if we were doing things, which relations don't do, they just sit there. But if we were doing things, we would do R first. We'd start with A comma B, and then we'd have a B, and then we would do the next relation to that. Now that it may not be well defined, but that's what it's called, SR. So SR is the composition. Our book uses this concatenation notation for composition, and some people do that, and some people put a little circle. So let me show you an alternative notation that you might see in other um, sources. So this little teeny circle between S and R. Okay. So the definition of this relation is kind of complicated. It involves a lot of set theory stuff. So SR is by definition the set of all pairs AC. So SR is going to be a subset of A cross C. There it is. It's an element of A cross C. And with the property is that there exists a little b in B. This doesn't tell you how to find it. It just, that's the property that you have to have. And the property that B has to have is that A comma B is in R and B comma C is in S. So that's the definition of this composition. It's, I'll bet that's probably one of the more complicated or most complicated set definitions that we've seen. So let's see it. It's got the brackets, so it's a set. It's a set of ordered pairs, one from A, one from C, and for that to happen, for that to be in the set, the test for A comma C to be in the set is whether there exists a B, so that A comma B is in the first relation and B comma C is in the second relation. That's pretty complicated, but that's the most precise way to state this. And so there's the situation. So that's the composition, and it is immediately useful for something that we are going to just go right into talking about. So the other way that we talk about relations is in terms of matrices, and there's a special thing that we can do that allows us to express composition in terms of matrix stuff that we looked at a little bit earlier. And so this is an important conceptual tool, and this will come up when we talk more about graphs. And so composition in terms of matrices. And I got to pull something out from behind my ears. I'm sorry, only one ear. And what we're using here is what's called Boolean arithmetic. Now, the short way to say this, short ways are great. You know, you use a few symbols, but then, whoa, what's going on with this? I mean, sometimes it takes a lot of symbols to tease out what this use of a few symbols means. And so the short version of Boolean arithmetic is we have the usual two arithmetic symbols, and I'm gonna be weird. You can make fun of me. One of the symbols that we use in arithmetic is horizontal and vertical line segments joined at their midpoint. So that's this little symbol here. Most people say plus, but we're not doing addition right now. We're doing an operation that has many of the same properties as addition, so we use the same symbol. In programming languages, in object-oriented languages, this would be called an overloaded symbol. So that's a thing that happens, and so there's the deal. And so the symbol that the operation that corresponds to the symbol that we ordinarily use for plus is OR. So that means that 1 plus 0, I'm going to say plus because everyone does. 1 plus 0 is 1, 0 plus 0 is 0, and 1 plus 1 is, wait for it, 1. That's because we're taking 1 to be true, and what we have here is true or true. Yes, that's true. So this is just kind of another way of expressing the truth table for or we use the truth table for or to do this operation. And the multiplication, the small dot centered vertically in the spacing of the formula, that's and. And so 1 and 1 is 0. I'm sorry, I said 1 and 1 and I wrote 1 and 0. So, and 1 and 1 is 1, and 0 and 0 is 0. So these are, again, the standard things from, where'd they go? From the truth table for and. And so, so when we do the matrix manipulation, instead of using ordinary common or garden variety arithmetic, we're going to use Boolean arithmetic. And so these little formulas that I wrote here, that's the definition of Boolean arithmetic. Everything's involving ones or zeros. And so this is an appropriate way of manipulating these kinds of numbers. They're not numbers, these kinds of objects. Anyway, now if we look back at the definition of a matrix for a relation, everything's 1 or 0. So in some sense, we're saying that if the pair A sub I, A sub j is part of the relation, then we put a true in the slot ij in the matrix. And if that's not in the relation, we put a false in that slot. So the ones and zeros here make sense as Booleans, not as numbers. So, so the deal here is that if you have, now this only works on A cross A. So if M is the matrix for a composition RR, where R is in A cross A. A lot of symbols running by there, so let's make sure we get them straight. So M is the name of the matrix, and the composition is RR. I guess the order doesn't matter here because they're the same, and it certainly matters up here, but it doesn't matter here. And R has to be a relation on A cross A. So the middle thing over up above, we had A cross B and B cross C, and so we started with A. We had to find a corresponding B that also had a C corresponding to that. This language is so much better. So now there's no issue with those kind of things because the pairs are element of A, and we're looking for an element of A so that we have element of A, and that's the way it goes. So if M is the matrix for a relation, then using Boolean arithmetic, the composition of the relation with itself. Now this is weird. So, so the composition of the relation with itself is RR or R squared or R circle R. Take your pick. And that is represented by, that's a relation on A cross A, and that's represented by the square of the matrix using Boolean arithmetic. Now we can compose R with R squared, and we'll find that R cubed is represented by M cubed. And in general, R to the J is represented by M to the J. So there's this very neat relationship between composition of relations and the matrix representation of the relation. And this is going to get to be a big deal when we start to talk about graphs. And so, well, wait a second, we're already talking about graphs. So we're saying we've got this graph represented by a matrix. Remember, that's called the adjacency matrix. And so the graph is a relation, and we could compose the relation, and that would give us a new graph. And then we could compose the relation again, and that would give us a new graph. And we could keep composing. And what happens there is when you compose, you have this pair represented by this lowest vertical piece, this vertical edge in the graph. That is an element in the relation, and then you go from the second one up here to this other one. That represents something in the relation, and the composition is that this one and this one. I guess I better circle them in red or something, so that they're these are now in the composition. These are a pair in the composition because you can go from A to B and B to C. So you've got AC, so that's in the composition. So this leads to a very interesting and useful operation that we can do, which is that we can call, this is what's called the transitive closure. Man, it had to be a mathematician who made up that word. And so what we're going to do is it's actually easiest to see in the partial order thing. So this is the matrix for the relation is the adjacency matrix for this partial order. So we're using different things, but we're talking about the same thing. So anyway, the idea that you want to get here is that by transitivity, this bottom one you can kind of trace along in the graph is related to this top one eventually. I mean, you have to do one composition to get to here, and another composition to get to here, and another composition to get to here. And so what happens with the well, let's start with the matrix, I guess. So what you're going to get is, and this, remember, we're doing Boolean arithmetic. The transitive closure of some relationship R, which is represented by M, is these are the matrix operations that we talked about earlier, but now they're being done in Boolean arithmetic. It's M plus M squared plus M cubed plus M to the fourth. So power for a matrix makes sense because M squared is M times M, M cubed is M times M times M, and so forth and so on. And the last one that you're going to need here is M to the order of the set. So there's the formula for transitive closure for the matrix of the transitive closure. And so remember, that's doing Boolean arithmetic. Let me highlight that. So this is Boolean arithmetic. So what's gone on here is you've got the ones that you were given, then you pair them up, and then you make little triple pass, 1, 2, 3, and then quadruple pass, 1, 2, 3, 4, and so forth and so on. So if you look at a more complicated Hasse diagram, you might have, 7 or 8 in the, you might have 10, you might have 10 million. But you'd have to remember to be doing the, sorry, I have a computer problem. You have to remember to be doing the matrix multiplication in Boolean arithmetic. Okay, so that's the transitive closure, and we'll see this again when we come to doing graph manipulations. And the next thing to talk about is functions. Functions are another special kind of relation, and they have really important consequences in computing, so we can look forward to that.